Hello, my name is Haya Shulman. I lead the Cybersecurity, Analytics and Defenses Department at Fraunhofer SIT Institute in the German National Research Center for Applied Cybersecurity, Athene. In this presentation, I will talk about the ownership validation in the Internet and specifically the new distributed domain validation procedure deployed by Let's Encrypt. I will show you that two central design issues of the distributed domain validation of Let's Encrypt make it vulnerable to downgrade attacks. First, the vantage points are selected from a fixed and a small set. And second, the way the vantage points select the nameservers when they perform domain validation in the target domain can be manipulated by a remote adversary. I will show you how these two observations can be used to launch downgrade attacks, which can then be exploited for issuing fraudulent certificates. So let's quickly look at ownership validation over domains, focusing on the most popular procedure for verifying ownership over domains. We then move on to explain the downgrade attacks against domain validation, and we'll show you our two-sided experimental evaluation for issuing fraudulent certificates, and finally we discuss countermeasures. So it is important to protect communication to services from eavesdropping adversaries. For this purpose, we use the public key infrastructure or PKI to identify the target server and use its keys to establish a secure communication to the server. The certificate that the server sends says who the owner of the domain is. Establishing the correct identity of the server is critical. Imagine you create cryptographic keys and you use a TLS to connect over a secure channel to some server, but it is the wrong host, for instance, one that is controlled by an adversary. So establishing the correct identity is therefore a critical step to protecting our communication to services on the Internet. It essentially should protect criminals from obtaining fraudulent certificates for domains that they do not own. So there are a number of ways for verifying ownership over domains. And we focus on domain validation since it is supported by most CAs. These CAs collectively control more than 95% of the certificates market. And the reason for such popularity of domain validation is that it is automated, fast, and cheap, sometimes even free. So how does it work? Before issuing certificates, the certificate authorities run domain validation against services in a domain that is to be certified. This is used to verify that the domain owner de facto controls the domain. To verify control, a CA generates a challenge, which the domain owner should integrate into the selected service in a domain. For instance, add the challenge in the TXT record to the zone file of the domain, or add the challenge to a directory on the website in the domain. And the CA then checks the presence of the challenge by querying the selected service in the target domain. Since the challenge was sent to the domain, a genuine owner can receive it and hence can respond correctly. However, an off-bus adversary that does not control the domain cannot receive the challenge and therefore should not be able to respond correctly. And that is the basic idea which underlies domain validation. Now, simple and cheap, unfortunately, it is not secure because two recent projects which were published independently in papers, one in Usenix 2018 and one in CCS, demonstrated two different approaches for off-bus attacks against domain validation of popular CAs. The idea is that the attacker hijacks the challenge sent by the CA to the domain during the domain validation, and this allows the attacker to respond with the correct challenge and demonstrate control over a domain that it doesn't legitimately own. Now that's a really significant issue, of course, because PKI is such a significant building block in the Internet. So Let's Encrypt was the first CA to react quickly to the disclosed vulnerabilities. Let's Encrypt is one of the fastest growing CAs in the PKI ecosystem. It has already issued over 1 billion certificates and serves over 200 million websites. So Let's Encrypt initiated efforts to enhance the security of domain validation, even against own paths, man-in-the-middle adversaries. So it is important to understand that a deployment by a certificates market leader such as Let's Encrypt is a huge step towards improving the security of domain validation. And in 2020, Let's Encrypt deployed in the production environment a mechanism called multi-VA, domain validation from multiple validation authorities, or vantage points. And here on the left side, you can see single validation authority which performs domain validation. It selects one of the name servers and it sends the requests and communication with this name server. On the right side, however, you see the multi-VA domain validation, and um, you see every validation authority sends the validation requests to a name server that it independently selected. And there are many name servers and many validation authorities. So currently, Let's Encrypt uses 4 validation authorities. Each runs a DNS resolver software for looking up resources and domains and for validating control over domains. When a request for a certificate arrives, the 4 validation authorities perform lookup of the target domain by sending queries to the name servers, which they select independently, and concurrently validate control over the domain. Now, the idea is that even strong on-pass adversaries have limited capabilities in practice. Yeah, so imagine on the left side, if an adversary hijacks the validation authority, then it hijacks all the communication, right? But on the right, this is not so. So the multi-VA assumes that the adversary may be able to hijack communication between some of the VAs, some of the name servers, but not all of them. So this, even if you hijack some of the VAs or some of the name servers, it does not suffice to foil the entire domain validation, since each validation authority independently selects the name server to which a query is sent. So to impersonate ownership during the domain validation, the adversary would need to hijack all the possible pairs of validation authorities and name servers. And here's an interesting question. How are the name servers selected? So the selection of the name servers considers performance, yeah? To ensure performance, as well as to balance the load of queries among the name servers, the DNS software implementations use different logic for selecting the name servers in the target domain. Domains typically use multiple name servers, on average 3, but a bit more than 3, but sometimes up to even 20 and more. And how does the DNS software select a name server in a domain to which a query is sent? The implementations typically prefer least latent and most available servers. To select the server, the DNS resolver monitors the performance of each name server in a domain and applies computation over the responsiveness of individual name servers, as well as the latency. And how do the VAs of Let's Encrypt select the name servers? To analyze this, we perform an experiment where we set up domains with name servers and we trigger queries to our domains. Our findings show that the queries are distributed among the name servers independent of the geolocation and of the network block on which the name servers are placed. Each VA sends a query to each name server with equal probability, and each of the name servers receives roughly an equivalent portion of the queries from each VA. So what happens when we introduce losses or high latency? We observed that the VAs distribute the queries among the name servers which have latency below 400 milliseconds uniformly at random. But we also saw that VAs avoid querying latent name servers or name servers with latency above 400 milliseconds, as well as name servers from which a VA experienced 2 to 3 consecutive packet losses. These name servers are avoided even for a period, such a long period like 15 minutes. So afterwards, the VAs will probe these name servers again to see if the performance improved, but 15 minutes it is blocked. We found this behavior to be identical to unbound DNS software. And that is the software that is used by Let's Encrypt. So this slide, you can see the behavior of different DNS software when responses are lost or arrive after high latency. We see that all the DNS software actually try to avoid poor performing name servers. And they all block name servers which lose responses into some periods of time. So using this observation, we develop a downgrade attack to force the VAs to query a specific attacker-selected name server. This allows us to reduce the domain validation again to just a single point. So our downgrade attack is carried out by reducing the number of available name servers each VA of Let's Encrypt can query, leaving just a single name server that all the VAs will query. The attacker uses startbot to request a certificate. This is how we start the experiment. This triggers lookups from the DNS resolvers at the 4 VAs of Let's Encrypt to the name servers in the target domain. The attacker causes the requests to all the name servers except one to timeout. Following a timeout, the VAs go into exponential backoff. And this exponential backoff depends on the length of the exponential backoff depends on the DNS software implementation. So DNS requests of unbound are retransmitted after RTO, retransmission timeout. And in case of an unbound, this is 376 milliseconds. You can see this on this slide, how the attacker uses the exponential backoff intervals to repeat the attack. Now the attacker repeats the attack every RTO, and then the query after its timeout is retransmitted to the next name server by the DNS software. However, after 2 consecutive losses, the name server is moved to infra cache, and its infra TTL is set to 900 seconds, which is 15 minutes. And this the attacker applies to all the VAs and all the name servers except one, causing all the VAs to block all but one name server. This is the only name server to which then the queries will be sent. So what is interesting is how to block losses in reality. It's not how to cause losses in reality. It's not so easy. It is, of course, easy to do with an on-pass adversary, say a compromised router which selectively drops packets. But can this be done with an off-pass adversary, which the packets do not traverse? And indeed, we developed techniques which allow this also with an off-pass adversary. These techniques introduce packet losses into the communication between the name servers and the VAs. The lost packets signal through the DNS software the VA connectivity problems at the name server. The name server is then blocked by the VA for 900 seconds, 15 minutes. So I'll show you 3 methodologies to do that. One methodology is low rate elimination. It is generic and applies to any domain and all name servers without assuming any properties. So it is illustrated on the right of this slide. The idea is to send bursts to the router that connects the network of the name server to the internet. The traffic bursts never reach the name server network, and they arrive at the router, they fill the buffer, and they cause the packets to be dropped, subsequent packets. So if the attacker synchronizes the burst with the query of the VAs, it will cause the router to simply drop the query of the VAs. We could not evaluate this methodology in the internet because it causes packet loss, but we evaluated it ethically in a controlled environment that we set up. We developed 2 other methodologies as well, which do not require so much traffic. One assumes that the name servers fragment the responses. The other requires that the name servers enforce rate limiting on inbound DNS requests. So let's start with the fragmentation. Fragment misassociation technique exploits fragmentation. It is illustrated on the left side. The attacker injects a spoofed fragment, which the IP defragmentation cache at the VA reassembles with a genuine fragment which arrives from the name server. So the name server sends a response which is fragmented, let's say, in 2 fragments. Once the first fragment arrives, it is reassembled with the fragment of the adversary, which is waiting in the IP defragmentation cache, and it goes then up to the transport layer. Now, we want this packet to be discarded. So we want to combine it construct it in such a way that the operating system will discard it. What we do is we create a wrong checksum. We simply do not try to match the checksum. As a result, the reassembled packet is discarded by the VA. The genuine second fragment from the name server does not have a matching first fragment, and hence it is discarded after a timeout of 30 seconds. But the point is that there is no response from the name server. The VA itself reassembled it incorrectly and discarded. This causes the pending query to timeout and is perceived by the DNS software on the VA as a loss event. The other technique, loss via excess query rate, exploits rate limiting on name servers. It is illustrated in the middle here on the slide. The adversary sends multiple requests to the target name server using a spoofed IP address, this time of the victim resolver. Now the rate limiting on the name server starts filtering of the incoming packets. The adversary issues request for a certificate from Let's Encrypt. When the request from the DNS of Let's Encrypt arrives at the name server, it is filtered. Now the victim DNS resolver perceives this lack of responses as an indication of poor performance of the name server and eventually avoids querying it. We found that 4,000 queries distributed over a second suffice to trigger rate limiting in servers that support rate limiting. And then the rate limiting is applied over the CADR/24 block. So we also experimentally evaluated these methodologies against the two methodologies which can be evaluated in the internet. We evaluated against our dataset of domains. We found that they apply to 24% of Let's Encrypt certified domains and 20% of almost 1 million top Alexa domains. So to identify domains which are vulnerable to these two methodologies, we performed the following. Let's start with fragmentation. To find name servers that return fragmented responses, we'll reduce the MTU of the name servers using an ICMP error message. We're ICMP type 3 code 4. This is fragmentation needed message. The adversary needs to cause the name server to fragment so that at least one byte is in the second fragment. We found that almost 2% of Let's Encrypt certified domains and 4%, a bit more than 4% of 857,000 top Alexa domains fragment responses and have also predictable IP ID allocation. This means that the adversary essentially can easily match a spoofed second fragment that would be reassembled with a genuine first fragment from the name server. Now, to find servers that apply rate limiting, we perform experiments sending 4,000 queries distributed over a period of 1 second. This is roughly equivalent to 2.5 megabit per second. Now, we find that the rate limit is typically reached within a second and is enforced in the subsequent 50 seconds. So even with this modest rate of 4K packet per second, we find that more than 24% of the name servers and top-level domains, and 23% of the name servers and Let's Encrypt certified domains, and 16% of the name servers in Alexa are vulnerable to elimination, name server elimination attack. Now finally, the generic methodology that applies to any domain, we could not test in the wild because of the performance downgrade that it would introduce. So we perform experiments in a controlled environment using popular routing platforms. And we use the default buffers which these routing platforms have. Our results are listed in this table on the slide, and you can see what is the burst size that should be sent to cause losses for different routers. Some of these routers, for instance, they're on the backbones are pretty large, and in reality, actually, the bursts can be even smaller than what is listed in the table. This is, for instance, due to processing and context switches and hardware, context switching in hardware, which introduce load on the router. Also, in reality, the operators often resize the buffers to smaller sizes. And finally, another issue is that there is traffic In the internet, there is also traffic from other sources, which also fills a queue on the routers. In our experiment, we used clean slate, so we only sent our traffic. Therefore, our evaluation pushes, of course, an upper bound. In reality, the adversary can send much smaller bursts. So now what we will do is we will combine our off-path downgrade attack with PGP subprefix hijacks to issue fraudulent certificates of Let's Encrypt for victim domains. To launch our attacks against real internet targets, we develop an ethical two-sided evaluation methodology. First, we launch our attacks. We launch our combined attack to issue fraudulent certificates with Let's Encrypt for our own victim domains, which we register and set up for that purpose. We use the setup that is illustrated in this figure, and the adversaries on one AES, Let's Encrypt vantage points on another, nameservers of the victim domains are also on different AESs. And in the first step, the adversary applies nameserver elimination methodologies to force all the VAs of Let's Encrypt to perform lookups and domain validation against just one specific nameserver of its choice. As an example, we select nameservers on networks which can be subprefix hijacked, because this is the vulnerability which we exploited in this work, but this could be anything. This could be a nameserver with a 0-day, for instance. So focusing on our nameservers which can be subprefix hijacked, we found that actually more than 10% of Let's Encrypt certified domains and 11% of Alexa domains are vulnerable to the attacks. And for them, it is possible to issue fraudulent certificates. Now, when we run evaluations against our own domain, which is using this nameservers on illustrated in figure left, we select nameserver 1 and S1 on prefix 22/16. This is the network which we own and control. And in second step, the adversary then uses certbot, submits requests for a certificate for our victim domain, and the attacker launches PGP prefix hijack to redirect the DNS packets to the attacker network, which is AS6. The attacker concludes this validation and receives the fraudulent certificate for our domain. This allows us to evaluate the attack, the complete attack, against our domain, between Let's Encrypt and our domain. And we run multiple execution of these attacks against our victim domains, and we plot the duration of the attack and figure on this slide. As you can see that 99% of the evaluations complete within 2 seconds. Now this plot measures the time from the issuance of a hijacking PGP announcement and until the fraudulent certificate is received. Now the question is, of course, are real domains in the internet vulnerable to our nameserver elimination techniques and to issuing fraudulent certificates? Do they have the required properties? So that was the first step, what I just showed you, of evaluation between our domains and Let's Encrypt. And now you see the second step, which is evaluation between the real victim domains and a CA which we control. So in this evaluation, we use our data set of domains, and these are real domains. Yeah, so we want to evaluate them ethically. We reproduce the exact setup of Let's Encrypt in a controlled environment set up by us. We create our own CA, we issue certificates for domains in our dataset with our CAs, and we then launch the combined attack to obtain fraudulent certificates signed by our CA for those domains. This allows us to identify domains with which the VAs of Let's Encrypt can be forced to query a server of attacker's choice, so that the nameserver can be subprefix hijacked by the attacker. The hijacking PGP announcements are sent locally only to the router that connects the network with our CA to the internet, and are not distributed in the internet to avoid impacting the global routing. We evaluate this attack, and you can see on the slides the number of vulnerable domains that we found. So what about the other CAs? We evaluate our attack methodologies also with other CAs. for a successful domain validation, actually only Let's Encrypt requires that multiple vantage points receive the same responses from multiple multiple vantage points. However, other CAs, even when they select an IP address from a large prefix, such as Google, for instance, they perform the validation using a single IP address. So all of our blocking methodologies apply to other CAs as well, and we only needed to apply slight modifications according to the behavior of the DNS software at each CA. For instance, the number of the required timeouts differs. You can see this in the timeouts column, as well as the length of the blocking interval. This is the block column, during which the DNS software avoids querying the blocked name server. So essentially, we show you that all the CAs are vulnerable to name server elimination, which exposes them to effective off-path attacks. Now, there are a number of things which CAs can do to prevent our attacks. Most importantly is an unpredictable selection of vantage points. This would prevent our attacks since the adversary would not know in advance which vantage points will be selected to perform the validation. If the set of vantage points is sufficiently large, the adversary will not be able to attack them all in advance efficiently. Now, we also recommend that the name server's selection procedure is made resilient by querying also poor performing name servers. This additional latency will not be significant in issuance of certificates. Finally, the attack would be made more difficult if you turn off the caches. This is not critical for issuing certificates. Preventing our specific attacks with sub-prefix hijack, you can protect BGP with RPKI. This, of course, doesn't prevent other attacks. And also, it's also helpful to try to detect fraudulent certificates with certificate transparency. Not all the monitors, however, reported our fraudulent certificates. This is important to note. So, to conclude, domain validation is critical for bootstrapping cryptography on the internet. After validating control over a domain, ACA generates a certificate which can be used to establish cryptographic material and protect communication between the clients and the server. In contrast to other means for verifying control over a domain, domain validation is automated and fast and cheap. So these benefits made domain validation very popular. However, the benefits of domain validation are also coupled with insecurity, and attacks in 2018 demonstrated that single VA domain validation is vulnerable to off-path attacks. Now, in this work, we showed that distributed domain validation that Let's Encrypt deployed to ensure security even against on-path adversaries is still vulnerable even against the weaker off-path adversaries. We developed off-path downgrade attacks to reduce the domain validation to be performed against a single attacker-selected server. And in our case, we used a server which can be sub-prefix hijacked. Now, after forcing the VAs of Let's Encrypt to query a single name server that resides on a network vulnerable to sub-prefix hijacks, we carried out attacks that and successfully issued fraudulent certificates for 10% of the domains in our dataset. Our work shows that domain validation, although simple, is not yet a resolved problem. Now, this presentation is based on a paper that is going to be published at CCS 2021 with my co-authors Michael Weidner and Tianxian Dai. It is called Let's Downgrade, Let's Encrypt. Thank you.